Am I audible now? Okay. So first of all, I would like to thank the organizers for giving me this chance. So in this talk, I will talk about pointed tensor categories and pointed Majid algebras. This is a joint work with Hualin Huang and Shivdat Kumar. So this is the outline of presentation. So first of all, the classification problem of finite tensor categories. So finite tensor categories and quasi-Hopf algebras are dual, we can say dual to each other. Quasi-Hopf algebras are generalization of Hopf algebras, and this notion was introduced by Drinfeld. These algebras are very useful in various areas of mathematics such as number theory, low dimensional topology, knot theory, quantum integrable systems, etc. Because of these numerous applications, these subjects motivated the classification problem of tensor categories. So many results have been found on the classification of elementary quasi-Hopf algebras over the field of complex numbers. Because of the complexity of the general classification problem, so most of the authors have done the work on elementary quasi-Hopf algebras, or dually we can say pointed Majid algebras. So but the most of the results found, they are over cyclic groups. So this is the first example, we can say we are providing new examples of pointed Majid algebras, and therefore new examples of finite pointed tensor categories whose group of invertible objects is not cyclic. So here we are dealing with the pointed Majid algebras over Klein's 4 group. We hope that this example will let some situation on the class of general finite abelian groups. So first here we are dealing with Klein's 4 group particularly. So first of all, the basics of tensor categories. So monoidal category is a sextuple where C is a category equipped with the functor. We have a functorial isomorphism. We have an object which is called unit in C, and we have two morphisms L and R, and satisfying the pentagon and triangle axiom. These are the compatibility conditions. So for example, the category sets of all sets is a monoidal category where the tensor product is Cartesian product. In this category, the Cartesian product will work as that bifunctor, and in this category the unit object will be the singleton sets. So in this way, this category of sets will form the monoidal category. The category of all vector spaces will form the monoidal category. So similarly, the representation of a group over a field K. Then if we have a monoidal category, a right dual, we can define a right dual and a left dual of an object. So right dual of an object is an object in the category such that we have two morphisms EX and IX, and these compositions are identity morphisms. Then we say this object as X star is a right dual of X. Similarly, we can define a concept of left dual in a category. So a monoidal category is called rigid if every object has left and right duals. A tensor category is a rigid monoidal category. That means in a tensor category we have right dual and left dual for each object. So for example, the vector space of all finite dimensional vector spaces, the category of all finite dimensional vector spaces is a tensor category. The dual object will be the usual dual space. Similarly, the representation category. So coming to the notion of pointed tensor categories. So first of all, a coalgebra is said to be pointed if any simple right C comodule is one dimensional, and a category is called pointed if every simple object in the category is invertible. Invertible means it has left and right dual. So, for example, the category of right comodules over a pointed Hopf algebra is a pointed tensor category. So, now I will come to the duality of tensor categories and the quasi-Hopf algebras. So, this is the reconstruction theorem. These assignments, these maps are inverse bijections between these finite tensor categories admitting a quasi-fiber functor and finite dimensional quasi-Hopf algebras over a field up to isomorphism. So, this is the duality we can say, and this is called the reconstruction theorem, as we are getting these quasi-Hopf algebras H from these categories using the quasi-fiber functor. So, now the Majid algebras or co-quasi-Hopf algebras, these are dual of quasi-Hopf algebras, and quasi-Hopf algebras are associative algebra with quasi-associative co-associative structure. So, roughly this notion is this quasi-Hopf algebra notion is a generalization of Hopf algebras. So, Majid algebra is a dual of this quasi-Hopf algebra, and this is primarily a co-associative co-algebra with a quasi-associative algebra structure. So, explicitly this H delta epsilon, this forms a co-algebra, and we have a multiplication map M and unit. Then we have this map phi, convolution invertible map, we called it as associator, such that this equality satisfy. So, this is the here we can say the multiplication is quasi associative up to this phi. Then this is the equality satisfied, must be satisfied by phi, and this ensures that the condition that phi to be a 3 cocycle in case of a group, and this is for phi to be a normalized. Moreover, we have the antimorphism S of coalgebra and functionals alpha beta such that these three are satisfied with the multiplication, and these S alpha beta are compatible with the multiplication and this phi. So, for example, if we have a group and a 3 cocycle phi on G, then we know that Kg forms a Hopf algebra, and if we endowed it with Sg as G inverse and alpha G as 1 and beta G with this map, then we can understand this Kg phi as a Majid algebra, because all the conditions will be satisfied automatically. This is the condition, this phi will satisfy as it is a 3 cocycle. So, Kg phi, so I will use this frequently. Kg phi is a Majid algebra. So, from this example it is clear. Now, we are coming to the definition of Hopf quivers, which is given by Sibils and Rosso. A quiver is, first of all, a quiver is an oriented graph. So, a quiver is said to be Hopf quiver if the corresponding path coalgebra KQ admits a graded Hopf algebra structure, and they told that these Hopf quivers can be determined by the ramification data of groups. What is the ramification data? A ramification data of the group G is a formal sum of conjugacy classes where these coefficients are non-negative integers. So, if this is a ramification datum on a group, then the corresponding Hopf quiver is defined as the set of vertices will be the group itself, and for each x in G and for each element in the conjugacy class, we have RC arrows from x to Cx. This RC is the coefficient of the conjugacy class C. For example, if simplest example, if we have Z2 and suppose this R is G. So, we have 2 elements in Z2, E, G. So, the quiver will look like like this. No, other way around. If suppose R is E, then this is the loop. So this work is mainly based upon the quiver approach for Majid algebras, which is developed by Hualin Huang in his recent works. So his first result says that if we have a quiver, then the path coalgebra KQ admits a graded Majid algebra structure if and only if Q is a half quiver. So this theorem tells us that what quivers can come up as the quivers of Majid algebras. Then if we have a pointed Majid algebra, then we have its graded version induced by the co-radical filtration, then there is a unique half quiver and a graded Majid algebra structure on this coalgebra such that this grade H can be embedded into this Majid algebra, which contains the space generated by vertices and space generated by arrows. So this theorem enables us to construct Majid algebras exhaustively on these half quivers. Then if we have a group and a 3 cocycle and we have a ramification datum of the group and Q is the associated half quiver with this ramification datum, then the path coalgebra admits a graded Majid algebra structure with this as the sub Majid algebra. We know that from that example that this forms a Majid algebra if and only if the space generated by arrows admits a KG phi Majid bimodule structure. I will come to this notion. And moreover, the set of such structures on KQ is in one-to-one correspondence with these bimodule structures. So in order to classify these Majid algebra structure, we can classify these Majid bimodule structures on the space generated by arrows. So what does it mean by a KG phi Majid bimodule? First of all, if this is a KG phi Majid bimodule, then it decomposes into these subspaces. This we can understand in the language of quiver, that this is the space containing the arrows starting from H and going to G. So these and the multiplication, the module structure satisfy these inequalities. So if we have a group and its conjugacy class is denoted by the round C. For each C, ZC denote the centralizer of any element GC. Phi tilde C, the corresponding 2 cocycle on ZC determined by phi. This represents the category of phi tilde C representations of ZC, and this is the twisted group algebra. Then we have the following equivalence of categories, where this is the category of Majid bimodule on KG phi Majid bimodule, and this because we want to classify these bimodules to get the Majid algebra structure, and this is equivalent to this category. So we can find in order to find this, we can find the module on this twisted group algebra. So coming to the Majid algebra structure over Kleins 4 group. So here our group is now Kleins 4 group, and first of all we should know what are the 3 cocycles on K4. So this result is given by Huang, Liu and Ye, that any normalized 3 cocycle on K4 is cohomologous to this. So as ABC vary in the set 0, 1, we have 8 cocycles, non-cohomologous cocycles on K4, and this will be trivial if all of ABC are 0, then so that we have 7 non-trivial 3 cocycles on K4. Then in order to classify the Majid algebra structure, we have to find out the Majid bimodule structure. So then, and in order to find out Majid bimodule structure, we can find these representations. So we found that if we have one V and W are the one dimensional module over these twisted group algebras with these actions, then the value of these scalars will be this: lambda 1 square will be minus 1 to the power a, lambda 2 square will be minus 1 to the, lambda 2 square will be 1, and mu 1 square will be this, and mu 2 square will be, this is mu 1 square and this is mu 2 square. So this will be the action. Now this is the ramification datum on G. What we have done, we have K4 generated by G1, G2. So any arbitrary ramification will look like this P, E, Q, G1, or notation is U there, I think. S, G1, G2. This is the identity of K4. So any arbitrary ramification will look like this. So in order to find out finite dimensional Majid algebras, what we did, first of all, we took this ramification. So this will be the Hofstadter corresponding to this ramification, and we calculated the Majid bimodule structure on the space generated by the arrows of this quiver. So if the space generated by y1 and x2, this will form the projective representations of G, and we can extend, if this is the action, then we can extend this action to get a Majid bimodule structure on this space. So I didn't write all the actions because there are so many arrows, and we have to write all the actions of G1, G2, G3. I didn't write it. So this is the idea of the proof. I am going to skip it. So this is the main result, first main result, that the Majid subalgebra generated by the arrows and vertices of that quiver corresponding to this ramification is finite dimensional if and only if these conditions hold. So this is the cocycle is depending on ABC. So these are the values of ABC, and corresponding are the conditions with depending on the cocycles. So these are 5, one is trivial, and in one case we are getting only infinite dimensional algebras. We have similar results on these quivers if we represent our K4 by the cross product of G1, G2 and G1, G2 and G2. Then for these quivers, we considered these quivers. Q and A are arbitrary integers. We found these results, that for these results the Majid algebra will be finite dimensional if and only if these conditions hold. Similarly, these results, for if we denote the if we represent K4 by G1 and G1, G2, and this is for G1, G2 and G2. So these are the results. Next, we prove that this quiver, the Majid algebra generated by the vertices and arrows of this quiver, this will look like, this is G1, E, this is G2, this is G1, G2. So all are connected. So this is the quiver, and this proposition says that the quiver provide no finite dimensional Majid algebras generated by the set of vertices and arrows of this quiver. So this implies that for these quivers the subalgebra will be infinite dimensional if any of these positive integers are greater than 1 because of this proposition. So this is the main classification result. If we have a finite dimensional, connected co-radically graded pointed Majid algebra with its set of group like elements as K4 and this associator phi, this phi ABC is in that proposition, the three co-cycle formula. So if H is generated in degrees 0 and 1, or in quiver theoretic approach we can say if H is generated by the set of vertices and arrows, then H is isomorphic to one of these structures. So for these co-cycle, if this is the value of ABC, then the H will be isomorphic to one of these. For this co-cycle, H will be isomorphic to one of these, and so on. So it was conjectured by Etinghoff and Jalaki that any finite pointed tensor category over a field of characteristic 0 is tensor generated by objects of length 2. So this result classifies the finite pointed tensor categories whose simple objects make the Kleins group on the field of complex number. Because I forgot to mention one thing. The reconstruction theorem, this was for the quasi-Hopf algebras. So similarly we can find the reconstruction theorem for dual of quasi-Hopf algebras, that is Majid algebras. So there is a bijection between these two. So these are the references for this work. Thank you.
Hey, I had a question, which is, so you're working with the Klein 4 group. Are there examples that have been done for other groups? Or
Yes. No, there are examples for cyclic groups.
For cyclic groups, but this is the first non-cyclic group example.
Yeah.
Okay.
Yeah.
Are there any other? Yeah.
So there are very few cases when it seems to be finite dimensional. So do you expect that if you go to other non-cyclic groups that are bigger than the Klein 4 group, that there will be almost no finite dimensional? Or not,
Yeah, maybe
or
we can get.
But do you think everything will be infinite dimensional then, or
Bigger than no, I don't think so. There may be finite dimensional structures for the group which are bigger than K4.
Okay, I think actually we've got to thank the speaker again and move on.